Okay, let's go ahead and get started. First of all, I have to apologize that I forgot to bring the stack of exams with me. I will do my best to remember on Thursday, but meanwhile, you can pick them up during office hours tomorrow. The midterms have been graded. The midterms have been regraded. The scores are on the course website. The grading breakdown is a little bit complicated because we need to correct a mistake. In particular, we realized that the requirement, the cardinal deadly sin requirement to write down an English description of the thing you're trying to evaluate with your dynamic programming algorithm had not been consistently enforced in the homeworks, and we felt that that would be too extreme to then suddenly enforce it in full effect on the midterm exams. So there are in fact two sets of grades. These are the grades that used the oops, you forgot to write the English, you get a 0. These, the ones further up, are you forgot to write down the English description, you lose 3 points. The scores that are recorded on Moodle reflect the new rubric. The posted solutions reflect the new rubric. The numbers that are actually written on the front page of your exam may or may not reflect the new rubric. So check with Moodle to make sure that what your actual score is. And I apologize for the confusion. When I compute the letter grades at the end of the semester, I'm going to use the old scores to compute averages and standard deviations and letter grade cutoffs. But then I'll use your new score to figure out where you fit into that. So this change will not lower anybody's grade, even though some people's grades went up, and that would normally skew the curve. So we'll avoid that. I do want to emphasize this one line. We mean it. Don't just say, here's an algorithm. Tell us in English what the algorithm is supposed to do, unless it is literally verbatim with no additional symbols what the homework says to do. And in particular, on any dynamic programming question that might show up, say, on the final exam, when you say something of ij, we want an English description that includes the words I and j in it. It tells you what this function is supposed to compute before you tell us how you actually compute it. Not a description of the recursive algorithm, but a specification of what the algorithm is supposed to compute. Doing this because this is a habit that you were supposed to have since you were small children. Like, if you suck your thumb during the exam, we'll give you a 0. It's that level of, no, really, tell us what you're doing. Okay. The averages, and remember these are the old averages. The mean score on among the undergraduates, the mean score on the midterm was a 26. Among the graduate students, it was slightly higher, but if you look at the course policies, the undergraduates, the ones who set the curve. So this is the curve that matters for estimating your grade. This is higher than usual for my exams. Part of this is because I essentially solved problem 3 twice in the review session. And so as expected, the scores on that were extremely high. But also that was a deliberate, there's a deliberate tuning of the exam because I felt that the homework that immediately preceded the exam was a bit brutal. So if I had to assign a grade today based on just your midterm 1 score, this is the grade that I would assign.
Is there any minus, things like that?
Yeah, you can split it up about a third of the A's or A pluses and about a third of the B's or B pluses, a third of the B's or B minuses. A pluses are special. The people who are in green, if you're not on an iPad, those are the ones who scored over 95%, and that would have been an automatic A plus. Those people are excluded from the curve. It's blue because the iPad thinks when you surf the web and you encounter any string of numbers whatsoever, it's probably a phone number. So I can, you know, call the Vatican or something. So in the past, I've seen it actually very common for students to have letter grades that vary between the first midterm and the end of the class by as much as a full letter grade, occasionally even more than that. So people who have scores in the upper 20s, an A is within reach. People who have scores in the mid-30s, a B is within reach. This is a very, very rough estimate because this is only 20% of the final course grade. So don't take this as gospel, either on the low end or on the high end. If your scores are down in this range, the 10 is equivalent to answering I don't know on every page. You should worry. Please feel free to come talk to me to decide, you know, if, I mean, I have seen students with this grade coming out of midterm 1 pull out a C+. But it takes some effort. Come talk to me, especially even if you're sure that you want to drop, because I'd like to understand what the problem is, to what extent this is something that I and the other members of the course staff could have done better to make the material clearer. Or if you decide you want to stick it out, come talk to me anyway, just to make sure that if there's something we can do better going forward, that we have an opportunity to do that. Are there any questions about the exam? And again, I have to apologize for this confusion about the grading rubric. We tried to balance, you know, fairness with sort of the point of the rubric. Okay. If not, the other administrative thing is that homework 6 is out. Somebody asked about this question during the review session, so now's the time to actually ask it. Notice that there's a rubric here that doesn't include any nuclear bombs. There are no mines that if you don't do this one little thing, you get a 0. But I do want to emphasize that if you use maximum flow algorithms, the things that we're talking about this week and next week, as a black box subroutine, which is what at least one of the problems in this homework will ask you to do, you do need to prove that you're using that subroutine correctly. And in fact, proving that you're using the subroutine correctly is often both the most difficult part of the problem and the most important, because it's easy to trick yourself into using these black boxes incorrectly. Especially because, and I point this out in the homework, there are usually 2 components to proving that one of these reductions is correct. So for example, if you're returning either true or false, you can't just confirm that the true answers are always correct. You also have to confirm that the false answers are always correct. Okay. I'll actually start going through examples of this idea on Thursday, and you'll see better then exactly the kind of thing we're looking for. Okay. So, if there are no other questions, then we'll continue talking about maximum flows. Okay, so the maximum flow problem you're given as an input a directed graph with vertices and edges. You're given two vertices, a source and a target in this vertex set, and you're given a capacity function that assigns a positive real number to every edge. S and T are called the source and target. The output, which is in the word output, the P comes after the U. No, it comes before the U. The output is a function from the edges to the non-negative reals. Let me actually just say to the reals, subject to the following constraints. For any edge, the flow from U to V is between 0 and the capacity from U to V. That's the so-called capacity constraints. For any node V, the total flow into V equals the total flow out of V, except at the source and at the target. So if you think of this graph as representing a network of pipes, at every connecting point where a bunch of pipes come together, whatever water goes into that connection also has to flow out. This conservation of mass.
Are you currently recording this?
Yes, I am currently recording this. I will double check, but yes, I am currently recording this. Thank you. Okay, and then these just specify what it means to be a flow. And then I want to maximize the value of the flow, which I can think of as the total flow into the target minus the total flow out of the target. Okay. So I'm going to inject water into the system at S. I'm going to eject water out of the system at T. Everywhere else, there are no leaks in the pipes. So I have to have conservation of mass at every node except the source and the target. Every pipe is rated for a certain maximum amount of flow that can go through it. If I try to push more water through that pipe, then the pipe will hold, the pipe will burst, and I will lose my job. On the other hand, you should think of these as one-directional pipes. You can't push a negative amount of water through anything. Okay? Now, the way we compute these things, we saw this on Thursday, is the so-called Ford-Fulkerson augmenting path algorithm. Named after Lester Ford and somebody Ferguson, who discovered this algorithm 60 years ago. So the idea is that I'm going to start by initializing a flow to 0 everywhere. Every edge is going to have a flow value of 0. And then I'm going to construct the residual graph G sub f, and then say while G sub f has a path from S to T, push flow along that path, which means I'm going to update F, the flow, and I'm going to update the residual graph, and then in the end I'm going to return the flow that I just computed. Okay, so the residual graph, G sub F, what this encodes is for every edge in my original input graph G, how much more flow can I push along that edge? And at the same time, for the reversal of any edge in the original graph G, it tells me how much more flow I can push along that reversed edge, which is equivalent to saying how much less flow can I push along the original edge. So remember, I've got two different inequalities that I have to satisfy. The flow has to be between these two values, 0 and the capacity. If the capacity is 10 and I've got 3 units of flow going through, I can push 7 more units of flow forward, or I can push 3 less units of flow forward, which I'm going to think of as 3 units of flow going backwards. Okay. So the formal definition of this is that the residual capacity of any edge is defined to either be the original capacity minus the current flow value, if this is a forward edge, or it's defined as the flow in the reverse thing if this is the reverse of an original edge. And so the residual graph contains, you think of it as, take the original graph, insert the reversal of every edge, compute these residual capacities, and then delete anything whose residual capacity is 0. And I can't push any more flow through the edge, I may as well just take the edge away. So, finding the path, pushing flow along it, updating these things, all these things take time, linear in the size of the graph. Constructing the residual graph, I need to spend a constant amount of time at every edge to decide what the residual capacity is on the original edge and what it is on the reversal. Just do that. Finding a path from S to T, this is the standard reachability problem. I can solve it using whatever for search. Once I've found the path, the amount of flow that I push along it is whatever the minimum capacity of any edge on that path is. So if I have a path through residual edges with capacity 2, 5, 3, 1, 7, 8, 4, the smallest number there is 1, so I can push 1 unit of flow through that path before I saturate another edge. That gives me the amount to flow along. Again, this is easy to compute in linear time. Updating the flow is just updating records attached to the edges. Updating the residual graph is, again, at most, recomputing everything from scratch. But in fact, you can just update the records associated with the edges. And I do this over and over again until I can't anymore. And then where we left off yesterday, or sorry, not yesterday, Thursday, was if I have integer capacities, then you can prove that every time you push flow through the graph, you're pushing at least 1 unit of flow, which means that the number of iterations is at most the actual maximum flow value. So the algorithm will, in fact, terminate. This is a terrible, terrible upper bound because you can create examples of graphs where, in fact, the graph has only a constant number of edges, but has, some very, very large capacities that are encoded in binary, which means this maximum flow value is going to be exponential in the number of bits that you need to write down the input. And so in the worst case, this running time, remember, it's not a function of the number of edges and number of vertices. It's exponential in the number of bits that you need to write down the input. Yes?
Update the flow. Like you said, you find the minimum and you update it along.
Yeah, I changed the flow values along the path, and then I may as well just change the residual capacities along the path and its reversal as well. So all that takes time linear in the number of edges in the path. But crudely, that's at most linear time in the total size of the graph. Okay. So this is exponential in the worst case. Again, exponential in the number of bits I need to write down the input. If I assume real capacities, then it's horrible. It's possible to get into infinite loops, and don't even converge don't even converge to a good approximation. In practice, this is not, the infinite loops and the lack of convergence is not really something that shows up very often in practice. It can rear its ugly head if you're doing floating point arithmetic and you're really bad about setting up you're really evil about setting up the problem, and you're really evil about making the choices about which path to augment on. This is more of a, if you really want to be able to prove things about what your algorithm is doing, this is a landmine that you have to avoid. But in practice, you may as well assume that your capacities are integers. It's not that strict an assumption. But this exponential runtime is really horrible. And so what I want to try to do today is talk a little bit about the structure of the things that we're computing in a way that will help us reason about algorithms a little bit better and then prove things about these things a little bit more easily. And discuss a couple of specific strategies to refine the Ford-Fulkerson algorithm. So in particular, Ford-Fulkerson doesn't specify which path we want to augment on. It just says, find me a path from S to T, and it leaves it up to the most incompetent pathfinding algorithm, or even worse, the most competent but evil pathfinding algorithm that you can imagine that wants to make the algorithm run slowly and can force this kind of exponential behavior or infinite loops in the real case. So I want to be a little bit smarter about how I choose that path. And one of the ways of choosing that path is going to be really obvious. The other one is a little bit less obvious, but turns out to be a little bit better. Okay. Now, the first, second, third, fourth, and fifth time I saw this, I had to go, well, this is a fire hose. You've just thrown 10 minutes of definitions at me. Before I go on, I need to pause and ask if people, have had a chance to kind of internalize what's going on. There are questions about what flows are. Are there questions about what residual graphs are? What the augmenting path algorithm is? Yes?
Just get like a brief overview of what residual graphs are.
Okay, so let me give you just a tiny example here. So this is not going to be as complicated as the examples we saw before. Okay, so here's S, here's T. I usually draw these arrows just to emphasize that they're the source and the target. Let's imagine that I have 5. These capacities. And then I'm going to send, say, 5 units of flow through this bottom path and 10 units of flow through this top path, and no flow is going through this center edge. Then my residual graph is going to have the same 4 vertices. There'll be an edge going backwards with capacity 5, because this lower left edge is full. The forward edge isn't going to show up because it doesn't have any residual capacity. In the lower right, I'll have a forward edge with capacity 5 and a backward edge with capacity 5. In the middle here, I'll just have a downward edge with capacity 10. In the upper left, I have a forward edge with capacity 5. I've got 5 units left, and a backward edge with capacity 10. And finally, in the upper right, I'll have a backward edge with capacity 10. And now, hopefully you can see there's an augmenting path from S to T that follows these 3 edges. The minimum capacity of any edge in that path is 5, so I can increase the flow values on those 3 edges. In this case, those 3 edges all happen to be edges in the original graph. That's not always going to be the case. But in this case, I can change this to 15, this to 5, and this to 10. And then when I do that, what happens is now this forward edge just vanishes entirely. The backward edge goes up to 15. This now becomes a pair of edges with capacity 5. The forward edge vanishes, and the backward edge in the lower right comes up with capacity 10. At this point, there are no more paths from S to T in the residual graph, and so the algorithm is done. That is maximum flow. Okay? All right. So, at a very, very high level, one way that you can think about what the Ford-Fulkerson algorithm does is, given a graph G, first I find any flow F in the graph G, and then I recursively find a maximum flow in the residual graph of F. So I let F prime be the maximum flow, in this case recursively computed by Ford-Fulkerson in this residual graph F, and then I'm going to return what I'm going to write as the sum of these 2 flows. Okay. So the way that Ford-Fulkerson is normally described, the first step, you're finding just a single path in the original graph. But in fact, you can think of this more generally as finding any flow at all. And what I'm sort of approaching here is that you can think of paths as a special case of flows. So if I have a graph, and in here I'm only going to draw the flow. I'm not going to talk about capacities for the moment. But if I have a path from S to T that looks like this, and I send 1 unit of flow along this path, this is a flow. This is a flow from S to T. Okay. Mass is conserved at every vertex other than S and T. This path doesn't necessarily have to go through every vertex in the graph. That's fine. But what I'm doing in the first step of Ford-Fulkerson is I'm finding a flow of this form. But more generally, I could just say, find me any flow. Then everything else that Ford-Fulkerson does, you can think of as happening recursively in the residual graph of what you just computed. And then you take the original flow and the residual flow that you find, and you add them together, being careful that, if in my original flow I found a 5, and recursively F prime I found a 3, well, that's great. I just return 8. But if in my original graph I found a 5, and in F prime I found a 3 going backwards, then when I say add, I mean, add with the appropriate sign. Right? So this is an addition of this is how you add flows. Okay. So in more generality, I mean, there are a couple of ways you can think about what's going on here. One of them is that the space of all flows in a particular graph, if you ignore capacities, if you ignore the capacity constraints, just talk about conservation, they're vector space. You can add them, you can scale them, you can find a basis for them, you can do all sorts of linear algebra stuff to them. I'm not going to talk about that view so much this time. But the other way that you can think of it is, instead of thinking of a path as a particular special case of a flow in here, is to turn that on its head and say, there's a sense in which I can think of any flow as a sum of a bunch of paths. Okay? So this is really what Ford-Fulkerson computes, is it computes a sequence of paths, and you add all these paths with the appropriate weights together, and you get the final flow value. Right? Get the final flow. Okay, so more generally, there's something called flow decomposition that says any flow f in any graph G can be written as a sum, let's say as a weighted sum of paths. Well, I have to be a little careful here, and cycles. Okay. So what I mean is, I may, have a path sitting here, and I'll send 5 units of flow along that path, and then I'll add in a cycle where I have 3 units of flow along that cycle, and then maybe I'll add in another path like this. And so the sum of these things is a flow where, for example, this top edge has 2 units of flow going to the right. This edge, this diagonal edge has 5 units of flow going up and to the right, and so on. So this imposes some structure on the flows which can be useful, because instead of just thinking of this flow thing as a function that you apply, every edge has a value, and there's some linear constraints. Instead, you can really think of the object that you're computing as a collection of paths and cycles. Now, the way Ford-Fulkerson works, you don't actually ever get cycles, but I said any flow, and there are flows which Ford-Fulkerson would never compute, at least in the way that it's phrased here. But I want to, we can actually, refine this flow decomposition thing a little bit further. If an edge from U to V appears in any path or cycle in this decomposition, then this is only possible if the flow value is positive. Okay, so there is a decomposition that never does this, that never has something going forward across an edge and something else going backwards across the same edge. So now we're leaving the realm of the kind of thing that Ford-Fulkerson computes and just sort of looking at the structure of flows in the abstract. This flow decomposition doesn't have this property, but nevertheless there's a different decomposition of exactly the same flow that does have this property. And the second thing is the total number of paths and cycles is at most the number of edges in the graph, which again is very different from what happens with Ford-Fulkerson. Because Ford-Fulkerson might end up producing this really enormous, exponentially large number of iterations before it converges, but nevertheless, there's a sense in which if Ford Fulkerson could just sort of look into the future and pick out the right paths to augment on, it could be done in only order iterations. Okay. If the flow has value 0, so if the flow has value 0, this is sometimes, flow with value 0 is sometimes called a circulation. So you should imagine now that instead of water going through pipes, you have blood going through arteries and veins in your body. Hopefully you don't have any places where blood's spurting out and other places where blood's coming in. It just moves around in your body. Always, you know, but whenever it goes into a connection where there's a branch in your veins, the same amount of blood coming in also goes out. A circulation, you can always just write as a sum of cycles. You never need to introduce any paths from S to T because S and T don't play any special role at all. On the other hand, if F is acyclic, meaning there are no cycles, if I just draw the graph as I've done here with just edges that carry flow, and there are no cycles in the flow, then I can write this as just a sum of paths from S to T. And I should have actually said all the paths up here in this decomposition start at S and end at T. Okay. The proof of this structural formula, this structural theorem, is straightforward by induction. Essentially, you can take any flow, and if it's a circulation, you can just sort of wander around in the flow until you hit yourself again, and there you found a cycle that you can subtract off. If you don't have any cycles, then you can just start at S and walk until eventually you will hit T. You can't get stuck in the middle because of conservation. It's conservation of mass. If you start at S and start following the flow forward, whenever you go into a vertex, you have to be able to come out of it again. And whenever you find one of these cycles or one of these paths, you do sort of the opposite of an augmentation step. You say, what's the minimum amount of flow among all the edges along this path? We'll just subtract that much flow from every edge in the path. And now you've got at least one edge that wasn't empty and is empty now. So every time I subtract off a path or I subtract off a cycle, I effectively reduce the number of edges in the graph by 1, and that gives us this upper bound. Yeah?
What do you mean by total in that line?
I mean the number of paths plus the number of cycles. Let me just write it that way.
Oh, that's a number sign.
Yeah, I'm sorry. Let me write this in a way that people can actually read. The number of paths in the decomposition plus the number of cycles in the decomposition is at most E. And in fact, if you play really careful games with it, you can even make that upper bound smaller, but you know, that we're not going to bother with that. Okay, so flows can be decomposed into paths and cycles. If the flow happens to be acyclic, you can just decompose it into flows. If the flow happens to have value 0, you can just decompose it into cycles. Now the interesting thing is that if you take this sum of paths and cycles and you just strike out all the cycles and you only sum up the paths, you'll get a flow with the same value because subtracting off a cycle doesn't change the amount, the total net flow going out of S, or the total net flow going into T. Which means that, you know, there's a corollary. There is a maximum flow that is acyclic. I can just compute a maximum flow. the proof of this theorem actually gives me an algorithm that identifies those paths and cycles, and I just erase all the cycles. And once I've removed all the cycles from the flow, surprise, surprise, the flow doesn't have any cycles in it. It's acyclic. And it's sometimes useful when you're applying maximum flows to be able to assume this. To be able to say, you know, I can wander through the graph, and the structure of the graph is a DAG. And you can do things that you would do to DAGs, like topological sort, to the output of a flow algorithm. Another corollary is we can compute this decomposition more or less by brute force in order VE time. And moreover, this running time, V times E, is the best we could possibly hope for. So there are flows, there are graphs, and you can find flows in these graphs where you really do need to use about E paths and cycles, and each of these paths and cycles goes through at least half of the vertices. So this V is really the best you could hope for. But that also means that any algorithm that incrementally computes flows by which, you know, incrementally I mean it computes the flow by finding a path or finding a cycle to push flow around. Just does that repeatedly until it computes a maximum flow. Requires at least that much time in the worst case. Because it's you can think of Ford-Fulkerson as an algorithm that, among other things, computes this flow decomposition. And the flow decomposition might be this big. So this is kind of a natural goal for how fast we would like flow algorithms to be. And in fact, there is a flow algorithm that maximum flow algorithm that runs in order VE time. It was published by an MIT researcher named Jim Orlin in 2013. I believe there may be 3 people on the planet who understand it completely, and I hope one of them is Jim Orlin. If you look in the notes, you'll find references, not actual descriptions, of several algorithms. They get within logs of this running time. So one of the things that you'll see if you look at the homework is this. You may assume that maximum flows can be computed in VE time. Just, it's a black box here. Okay. So that's what you write on your cheat sheet. That's what you just say, by Orlin's algorithm, or just because Jeff said so, you know, VE times. Okay. So any questions about this kind of flow structure? Yeah.
Well, can you just explain the third bullet point again, or maybe draw a picture or something? I'm not really sure what it means.
Oh, okay. So a circulation is a flow that doesn't start or end anywhere. It just wanders around. So again, I'll draw a 4-node example. Here's 10. I'll send 5 there, and 5 there, and 5 there, 10 there. Okay. So here's S and T. Not that it matters. This is a flow with value 0 because the net flow into S. So I have 10 units of flow out and 10 units of flow in. They cancel. The net flow out of S is 0. Net flow into T is 0. So I've actually conservation at every node in the graph. So this particular circulation can actually be decomposed into 2 cycles, each carrying 5 units of flow. Or sorry, I've done that wrong. Not this one, but this one. Okay, so this is the sum of a cycle that follows this triangle that carries 5 units of flow, and another cycle that goes all the way around the outside carrying 5 units of flow. Okay, good. Yeah. Sorry. Yes, I'm sorry.
Can you go back up to the decomposition graph? Can you just basically explain the extra code there, Tom?
I'm sorry.
Just the graph, the initial nodes right there.
Oh, so I'm imagining here. So I was just drawing drawing a bunch of paths and cycles in some graph that has at least 5 nodes.
Oh.
Right. In fact, I could just easily have the graph with at least 6 nodes, and just the flow no flow goes in or out of this vertex. So.
Oh, I see.
Okay. All right. So let's try to be smarter about augmenting. So the kind of example where you get really awful behavior is something that looks like this. Right. So here's a 5-node graph. Source and target are the top and bottom. I've got 2 other edges. X is some really big number. The way that I can create the worst case behavior is the first time I augment, I'm going to augment along this path, and I can only push 1 unit of flow. Then what happens in the residual graph is this middle edge flips and now points the other way. And in the second augmenting step, I'll push 1 unit of flow this way. And now, effectively, what I've done is I've reduced all the x's by 1 and left the middle edge alone. And so I'm going to need x more iterations of that before I'm done. Okay.
2x.
2. Well, x more iterations of the pair of augmenting. Yeah. So altogether, I'm going to be doing 2x augmentation steps. But that was kind of stupid, because you can look at this graph immediately and say, well, why did I take this detour? I should have just gone this way and pushed x units of flow, and then gone far to the right and pushed x more units of flow, and then I'm done. Okay? So can we think of a way to sort of generalize in what way taking these paths on the far left and far right was smarter than taking the zigzag path through the middle? Yeah.
We use flows with the highest capacity.
Okay, so this is the one that everybody thinks of first. This is what I call the fat pipes heuristic. I want to push along the path in the residual graph with maximum capacity. Right. This, by the way, is due to Edmonds and Karp in I think sometime in the early 70s. So it turns out that doing this find the maximum capacity path that you can and push flow along it, essentially pushing flow greedily, does create a substantial improvement in the running time. And in particular, at least with real capacities, you might still end up in infinite loops, but at least you'll converge to the right answer. Okay? So it's not the ultimate result that we want, but it's better. Yeah?
How do you know all the passes there?
I'm sorry?
How do you know all the passes from S to T?
I don't understand. You're given the graph. What do you mean by know all the paths from S to T?
I mean, you have to calculate all the passes there, right?
No, I just have to calculate the one that has the largest capacity.
Then how do you copy the one that has the largest capacity?
I modify Dijkstra's algorithm. This is a good exam problem. Think about it for 5 minutes. Right? So Dijkstra's algorithm, you have this expanding wavefront, and you define the distance to a node that's inside your wavefront, and when you expand, you add. Instead of adding, you take a min.
Yeah, I see.
Okay. So it's possible to actually, we can actually compute this path in time proportional to E log E. You know, roughly the running time of Dijkstra's algorithm, or the running time of the Yarnik-Prim minimum spanning tree algorithm, which is the same idea of growing a tree. So you just grow a tree from S, where instead of trying to minimize the total length of the paths, you're trying to minimize the minimum capacity on any path, or maximize the minimum capacity. Okay. So it's slightly slower to choose this path than it is just to run with whatever for search, but you know, logs we can usually tolerate without too much difficulty. The question is, how many iterations does this algorithm need? So let me assume, because I actually need to, I'm going to assume integer capacities. And I'm going to assume that the maximum flow value in G, I'm just going to call this capital F. Right? This is the value of the maximum flow in the original network. In this example, capital F is equal to 2x. Okay? So I want to argue that there is a path whose capacity is large in a way that I can quantify. Okay? So let's take F star to be any maximum flow. Now, this flow could be decomposed into paths and cycles. Okay? I can decompose into, at most, E paths. Maybe there's some cycles in it. Okay? And moreover, each of these paths only runs in the same direction as the flow, F star. So in particular, that means that if I take, each of these paths is sending a certain amount of flow, and if I sum up those amounts, I'm going to get the value of the total flow, F star. So I've got E paths carrying a total of capital F flow. That means at least one of these paths must carry at least F over E flow. Right? If I've got 10 people and together they have at least $1 million, I know somebody's got at least $100,000. This is Markov's inequality, if you want to think of it that way, or it's pigeonhole principle, if you want to think of it that way, or it's just averaging, if you want to think of it that way. So one of these paths has capacity at least F over E. So I know that there is a path from S to T in the original graph that has capacity at least 1 over E times the maximum flow value. But that implies that the fattest path has capacity at least F over E. Whatever path this E log E time algorithm computes has the largest capacity of any path, and in particular, the capacity of the path has to be at least the capacity of the fattest path in my decomposition of whatever max flow I picked out of thin air. Okay? So again, this is F divided by E. Okay, so what does this mean? So let's augment the flow along this path. And after we augment, we're going to, along that path, we're going to recursively compute the maximum flow in the residual graph of what's left. But so I get, capital F is, the maximum flow value in the residual graph plus F over E, right? I could take my maximum flow and decompose it into that single path and recursively whatever the maximum flow is in the residual graph. So the values also we're going to sum up the right way. But now if I reverse this, then it means that max flow of G sub F is at most 1 minus 1 over E times the maximum flow in the original graph. And this is the key to the analysis. Okay. Every time I push flow along the fattest path in the graph, I reduce the maximum flow in the remaining residual graph by at least a factor of 1 minus 1 over E. Now that's not a particularly large factor. If I have a graph with 100 edges, that means I have at most 99% of the flow left. If I have a graph with 10,000 edges, I have at least 99.99% of the flow left. There's the world's most useful inequality can come into play here. This is at most E to the 1 over E times the maximum flow in the original graph. And in particular, this means that after I've repeated this find the fattest path, augment k times, after k iterations, now the maximum flow that I have left in my graph is at most E to the minus k over E times, well, let me just write capital F here. Okay. So now I want to do something that will let me derive a good value for k here. That says after some value k iterations, the maximum flow that I have left is so small that I know the algorithm must have already stopped. So, in particular, if I can find a value for k such that this bound is strictly less than 1, then I claim if I can find the appropriate value of k that makes this the remaining maximum flow value less than 1, at this point the algorithm has halted. Why? Because I started off at the very beginning saying assume integer capacities. And as we saw last time, if you run Ford-Fulkerson in a graph that has integer capacities, then every time you push flow, you're pushing an integer amount of flow. And so the capacities remain integers. And so this maximum flow value over here on the left must be an integer. And it must be greater than or equal to 0. And there's only one integer that is greater than or equal to 0 and less than 1. 0. So what value of k would actually work here? let's see, I think it's when k is equal to f times the natural log, sorry, e times the natural log of f. All right, so if I set k to be, well, okay, plus 1. If I set k to be e to the natural log f, up here the e's are going to cancel, and I'm just going to get e to the minus natural log of f, which is 1 over f. Multiply that by f, I get 1. If I just add 1 here, I'm going to get at most 1 over e, and that's less than 1. Okay? So that means altogether the algorithm runs in e squared log e log f time. Because each iteration takes e log e time, and I multiply by this number of iterations. Okay. Now, per iteration, as I said before, per iteration, this is a little bit smaller. With the standard form Fulkerson algorithm, you get something that's just basically e times f. Here you get an e squared, and there's an extra log. But on the other hand, if you think of the input as being encoded in binary, this is actually a polynomial time algorithm, because you're only depending on the log of the flow values rather than the flow value as a number. On the other hand, as I said, if you look at the very end of the maximum flow notes, there's an exercise which I've never been brave enough to actually assign that walks through an example that shows that even this algorithm can get stuck in an infinite loop. But the analysis at least guarantees that the longer you run the algorithm, the less and less residual flow you have left, which means you are actually converging to the right value. Okay. In the most simple case, where all of the capacities are equal to 1, this is not particularly good because the original Fulkerson algorithm would give you a running time of e times f, and f is at most v, so e times v, whereas this gives you something that's closer to e squared with some extra logs. So this is actually not the best choice when you know all the capacitors are small. Yeah. Okay, so this is max flow open paren graph close paren is the value of the maximum flow in that graph. Okay, it's a number. So in this example here, max flow of this graph is 2x.
So what about GF?
GF is the residual graph for the current flow f. Okay. So this was better, but not great. I claim that there's another way that walking around that zigzag was not the smartest choice. And this is a little bit further away from intuition, but maybe I should say this in a slightly different way. Is there some other feature that the paths that go around just to the left or just to the right have that's different from the path that zigzags through the middle of the graph?
That's small. The number of edges is smaller.
The number of edges is smaller. Right? So it turns out that if you actually really want an algorithm where the running time doesn't depend on the flow value at all, then you should look for shortest paths from S to T. Now, when I talk about shortest paths in this context, there's one thing to keep in mind. Normally, when you're thinking about the input to Dijkstra's algorithm, you have a directed graph, you have numbers attached to the edges that represent the length of that edge, and you sum up these numbers to get the length of the path. And here you're in a context where you have a directed graph and you have numbers attached to the edges, but those numbers do not represent the length of the path. If anything, the right way to think of these is those numbers represent the width of the edges. The length of an edge is 1. Okay? So the way that you compute shortest paths in this context is by using breadth first search. You don't need to run Dijkstra because every edge has exactly the same weight. You just throw things into a FIFO queue and branch out. Okay. Which means that I can find the shortest path in linear time. And in fact, it's not even like I really have to change the way I think about Ford-Fulkerson when I'm doing this. Because the way that the generic Ford-Fulkerson algorithm works is I just need to find any old path from S to T. And so you trot out your handy-dandy whatever first search algorithm, and you set whatever to be breadth. Okay. If you use depth first search, it's not going to work.
So what do we want to use as shortest points?
These are the augmenting paths. Remember, Ford-Fulkerson says find a path from S to T in the residual graph. Which path? The shortest one. The one with the minimum number of edges. Okay. So you can say this a little bit more explicitly. Find the shortest path from S to T in the current residual graph. And the only difference in the previous presentation of Ford-Fulkerson is that in the previous presentation, this was the word any. Now I'm finding the shortest. I should also point out that because we're doing breadth first search, there are multiple answers to this. So this is an example where English is a little bit incompatible with mathematics. Normally in English, when you say shortest, you mean the one shortest one that's shorter than everybody else. There's only one winner. In the context of these kinds of graph algorithms, there may be multiple paths with the same minimum length. Any one of them is a shortest path, and any one of them will do for purposes of this heuristic. Yeah. Okay, so I'm only going to have time in the next 5 minutes to give you what the intuition is. The intuition is kind of tied up in the analysis. And so it may be a little bit of a stretch to call what I'm about to tell you intuition, because when you just see it presented for the first time, it's not clear why the claims I'm about to make are true. Hopefully, though, once I've stated those claims, you'll have some idea of why this might lead to an efficient algorithm. Okay. So, the basic intuition is that over time, nodes in the graph get further away from the source. Right? So if you remember the Bellman-Ford shortest path algorithm, one of the ways of describing that algorithm was look at every edge in the graph, and if it happens to be tense, relax it. Look at every edge in the graph, if it happens to be tense, relax it. And the invariant that you're maintaining in that algorithm is that after k passes through the graph, you've essentially you've considered all possible paths from S to any other vertex that has at most k edges. And you need multiple passes to consider paths with more and more edges that might nonetheless be shorter because we have weights. The same thing is true here. Because I'm pushing flow along these shortest paths, whenever I push flow along the shortest path, I'm going to augment an edge, and that edge is going to vanish from the residual graph. And that's going to make it harder to traverse that path. I'm going to have to go around. And so if I want to formalize this, I can say let G sub I be the residual graph after I iterations of this algorithm. I'll define the distance from sub I of V. This is the distance from S to V in this ith residual graph. And the first claim is that these distances only get bigger. They can never get smaller. And for all vertices V and for all integers I, the longer you run the algorithm, the further away the vertex gets from the source. Now there's an equal sign here. That means that sometimes the distances don't change. But another way to say this, the second observation is whenever you saturate an edge in the graph, whenever you fill up an edge to its capacity, so let me say it this way. If the ith iteration saturates some edge from U to V, then the distance I of V is strictly greater than the distance at iteration I minus 1 of V. Okay. So at every iteration of the algorithm, I saturate some edge, and the endpoint on the far end of that edge is now further away than it used to be. That means after, at most, EV iterations, sorry. Well, okay. Let me refer to the notes for the technical thing here. I realize this statement is intuition, but not actually fact. Right? Morally, this is what's going on. I have to be a little bit. If I wanted to state this a little bit more carefully, it would take up more time. But essentially, every time you saturate something, something gets further away. Every time something gets further away, and you've got so many vertices, after this many iterations, the distance to every vertex is more than the number of vertices in the graph, which is impossible. Which means the algorithm must have halted by now. Okay, so after some fairly large number of iterations, I get a contradiction, which means that the algorithm actually halts. Sorry, if I have more than EV iterations, I get a contradiction. After at most EV iterations, and therefore the running time of the algorithm is just a polynomial in E and V. Yeah?
So what was the contradiction?
So the contradiction is some vertex has distance greater than V from the source. But that's impossible because every path in every graph has at most V minus 1 edges. So if you look at let me just pull up the one page of the notes really quick, and I'll just point at it. There's a list of a bunch of algorithms that None of which will be on your homework or exams. In fact, none of the details of the algorithms that I've showed you here. The idea is, we might ask you to prove things that are related to this, but we don't expect you to remember the details. We just want to explain that it can do. There's a bunch of stuff. These are only algorithms that have a running time that depends only on V and E and not on other parameters like the maximum capacity or the maximum flow value. In the newest version of the notes, there's another one that came out a couple of years ago that I need to stick in here. Here's Orland's algorithm. These are all really cool things for a different class. Just that, lots of cool ways of doing things, but we're not going to have time to talk about them. The one that you want to remember is that one. Or maybe I should say that one.
All right.
All right. Thanks.